Hello and welcome everybody to the Energy Simulation Rio de Janeiro 2025. My name is Karen Calderon Moreno. I'm a master's student of the University of Alberta. I am working with the Reservoir Geomechanics Research Group under the supervision of Dr. Gonzalo Zambrano and Dr. Richard Attorney. Today, I'm going to present my research, which is titled Thermohydromechanical Modeling to Evaluate joule-thomson cooling impact in a thin, highly depleted gas reservoir in Alberta, also called the AMIGO project. As a background, we know that carbon capture and storage is a key technology for reducing CO2 emissions from significant industrial and energy sources by capturing and permanently storing CO2 in underground geological formations. Preferred storage sites for these projects include depleted oil and gas reservoirs, deep saline aquifers, and other secure formations, offering cost effectiveness, accessibility, and lower environmental risk compared with other alternatives. CCS allows continual industrial activity while lowering emissions and could contribute up to 20% of the global reduction needed by 2050. Without doing this cost could increase as much as up to 70% of it. Depleted oil and gas reservoirs are among the most promising sites for CO2 storage because of decades of geological data proving sealing integrity and existing infrastructure that can lower the capex of the projects. The oil and gas industry extensive experience with CO2 injection using during enhanced oil recovery offers valuable operational knowledge. CO2 injection not only supports storage, but can also enhance oil recovery by decreasing viscosity and interfacial tension of it. These reservoirs had demonstrated long-term ability to contain fluids over millions of years, and in many cases, CO2 can occupy the pore space that was occupied by hydrocarbons, which could enhance the predictability in storage modeling. Globally, depleted gas reservoirs could potentially store up to 1,300 gigatons of CO2, with a practical capacity estimated at around 390 gigatons of CO2. However, understanding CO2 behavior after injection is vital to ensuring effective long-term storage. So, the purpose of my project. CO2 injection changes surface stresses conditions throughout pore pressure increases, temperature changes, and fluid rock interactions, potentially affecting the integrity of both the reservoir and the cut rock. Higher pore pressures decrease effective stresses, potentially reactivating faults, inducing new fractures, and triggering seismic activity, especially in faulted formations. Injecting cooler CO2 creates thermal stresses, leading to rock contraction, thermal fracturing, and stresses redistribution. Near the wellbore, the joule-thomson cooling effect causes a significant temperature drop as CO2 expands from high pressure in the wellhead to lower pressure inside the reservoir, particularly in depleted reservoirs, intensifying the cooling-related stresses. These thermohydromechanical effects may improve the injectivity, but also could cause risk of fracture propagation in the caprock. And repeated thermal cycling can cause degradation of the cement and casing, thereby increasing the risk of CO2 leakage throughout the surface. So, an effective thermohydromechanical model and site-specific geomechanical assessments are essential for ensuring long-term storage security. So now I'm going to present the methodology that we follow for my research. This methodology we divided in two sections. One section is the one that we use it for the flow dynamic model, and the other section is the one used for the thermohydromechanical model. So for the fluid flow model, we start by first getting the static model created by GLJ, and they provide us a coarse model and a refined model. We decided to stay with the coarse model in order to speed up runtime simulation. We import this static model into CMG, and then we start using and importing the static petrophysical parameters when we include the thermodynamic fluid model, rock fluid model, the initialization parameters, wells production data, and then we can get the history matching production rate and depleted pressure. For this model, we had a geometry of a total cells of 544,000 with active cells of around 240,000. As initial parameters or initial values that we know are the initial pressure that is around 27 kPa, 27,000 kPa. The reference depth is around 2 meters. The reservoir temperature is around 98 Celsius, a maximum saturation of gas of 0.8, and a water gas contact at around 2 meters. Together with this, we also use the reservoir properties when we have that the porosity goes from 0.01% to around 27%. The permeability in I goes from 0.02 millidarcy to 2000 millidarcy. The permeability in K goes from 0.0001 millidarcy to around 65 millidarcy. And the initial water saturation goes from 11% to 100%. Having all these parameters and reservoir properties, we imported them into our reservoir model in GEM, and here you can see how our model looks like at the end. Having our petrophysical model ready, we create and we imported the 79 producer wells. When we add the perforations and trajectories for these wells, we located our injector well, and using the data available in GeoScout, we were able to get from these 79 wells the gas and water production rate from 1963 to 2024. Having this data, we imported into GEN, and we create the constraints of maximum production rate and a minimum borehole pressure of 200 kPa. This is our model. At this point, our model was ready, and then we can start doing the history matching. Also, when our model was ready, we did an isothermal model in order to find out the maximum of the storage, the CO2 storage capacity of our field, and a non-isothermal model in order to evaluate the cooling impact of the CO2 in the reservoir. Then, when our model was ready and the history matching is done, we can move to the second part of the methodology, that is the thermohydromechanical submodel methodology, that is in order to evaluate the joule-thomson cooling effect. For this, we decided to stay with a submodel of 1 kilometer around the target well. Having the submodel, we needed to account for the removed volume that we didn't take into our submodel. So we add volume multipliers in our submodel in order to get into account the removed volume from the field. With that, we add our cap-rub, and for this one, we added 50 meters of cap-rub, and we used a porosity of 0.001 for our cap-rub. With the cap-rub ready, we refine around the wellbore in order to have a more precise plume and be able to analyze and interpret the plume behavior of the CO2 around the wellbore. Having our submodel ready, then we can create the flow files and the mechanical files in order to do our coupling model where we are going to use FLAG 3D and GenCMG, and we are going to couple this software together in order to be running simultaneously and being feeding back and forth pore pressures, temperatures, and updated permeability for the different injection scenarios. And at this point, we will be able to evaluate the impact of the cooling effect in the reservoir, especially in the carb. Now I'm going to present the numerical simulation results that we have so far. For this, first I'm going to start talking about the history machine. That is the history machine for our entire field. So here in this plot, you can see that is the total cumulative gas producing from 1963 to 2024. And the blue trend is the field history, and the orange trend is the simulated one, where we can see a difference of 0.8% between these two values, which shows that our simulated model is pretty accurate and really close to the real history of the field. Then we move to one of the most important parameters in order to do CO2 storage in a depleted gas reservoir. That is our average field pressure. And the same, the blue trend is the field history and the orange trend is the simulated one, which at the end we target for the history. We knew that the actually depleted pressure of our field is 314 psi, and from the simulated one we go 304 psi, which gives us a difference of 10 psi. And this is pretty okay, like it's a really low error, which gives us a really good accurate simulated field. Now we also want to present the results for our target well. So here in this plot we have gas production rate simulated, gas production rate history that are the circled one, and we can see that they really match to each other. We also add the bottom hole temperature and we can see that it drops 0.57 Celsius, as well as the bottom hole pressure, and it dropped 1,544 kPa. So these are the results for our target well, which is ready to have injection of CO2. Now, from the isothermal and non-isothermal models, we got the following results for CO2 injection in the entire field. So I'm going to start first with the isothermal results. That the goal with the isothermal results is to be able to get a general overview of how much storage capacity our well is going to have, our field is going to be able to have. So for this one, we run different injection rates, and we did it in the coarser model and in the finer model to see if we get any discrepancies between these two, but we got the same values, and we got the different storage capacity depends on the CO2 rate injected at that model. And for the non-isothermal model, we did two scenarios. One scenario when our well held temperature was 10 Celsius and the other one is 40 Celsius. So here I'm presenting the results for the scenario number one, where the temperature of the CO2 at the wellhead is 10 Celsius. And we can see different injection rates. We can appreciate that the cooling effect for the rate of 10 kilograms of CO2 by second is just 300 meters around the wellbore. But when we increase the rate up to 50 kilograms per second, we get a cooling effect of 700 meters around the wellbore. So this gives us an overview of how the cooling effect is going to be impacting the entire field. But if we need to really focus and get more detail how is this really impacting, we need to do the thermohydromechanical model. And for that model, so far we had the following results. We already get the SUD model at the volumes modifiers that is, they count for 0.4 of the volume that was removed. We added the carb, we refined it, and in this plot where we had average pressure and years, we can see that the models really overlap one to each other, meaning that our submodel is really reflecting the same behavior that the entire field submodel was reflecting, and we are ready to couple it and run the different injection scenarios to account for the cooling effect. As the results that we expect to get, we also want to get pressure distribution, temperature distribution, and minimum effective distribution around the wellbore under different injection scenarios as we did for the entire field. This is a work in progress, so maybe next year I'm going to be able to present to you the final results. That's everything for now. Thank you so much for your time, and I hope that you like it.